Okay, good day. Coshocton High School, Mathematics, Honors Algebra 2. I am Mr. McColley. This is the presentation for Lesson 4.2 for our Blended Learning Day on February 3rd, 2022. Let's get right to it. Today we are going to be talking about powers of binomials, and we're going to be multiplying some binomials out using Pascal's triangle and the binomial theorem to expand powers of binomials. But before we get to that, let's talk a little demonstration, and I want you to see this, and I'm going to have you pause here in a second and see if you can find the pattern. And so here's what I'm going to do. I'm going to go a 1 here, and then I'm going to go 1 and then 1, and then I'm going to go 1 2 1, and I'm going to go 1 3 3 1, and I'm going to go 1 4 6 4 1, and then I'm going to go 1 5 10 10 5 1. And then here's what I want you to do. Pause the video for a second and see if you can come up with the next row based on the pattern that I've already shown there. So what I want you to do after a countdown, I want you to pause the video and then see if you can come up with the next row, and then unpause the video, come back once you've come up with the next row and see if you figured it out. So 3 2 1, pause. Okay, and you're back. Let's see. Did you get the correct row? It is 1, 6, 15, 20, 15, 6, and then 1. And so how am I getting these rows? Well, you'll notice they're a little bit offset from each other. And if I take the two values from above it and add them together, I get the one below it. So to get this 5, I took the 1 and the 4 and I added them together. To get this 20, I added the two 10s together. So hopefully you got that. So Pascal's triangle is a method for finding coefficients for an expanded exponential form of a binomial. And note the first row is denoted with a 0. In fact, in each row, when we start counting the terms, we start counting with 0. And I know that's odd. Normally you start counting 1, 2, 3, 4. But in this case, we're going to start counting with 0. So this is the 0 row. And then when we get to the first row, when we count the terms, we start counting with 0. So we go 0, 1. In the second row, we go 0, 1, 2. The third row, 0, 1, 2, 3. And the fourth row, 0, 1, 2, 3, 4. So even though there's 5 terms there, we start counting with 0. And that's going to become important later on. My first example here is to expand the binomial and compare it to the coefficients in Pascal's triangle. Now when you multiply out a binomial to the third power, we have to multiply this thing x plus y by itself 3 times. So I'm going to write that out. So it's x plus y times x plus y times x plus y. I'm going to multiply these first two first, and if you remember from yesterday, I'm going to stack. So I've got x times x is x squared, and then x times y is xy, and then y times x is also xy, and then y times y is y squared, and when I add those up, I'll have x squared plus 2xy plus y squared, and then I have to bring this down, and I'm going to multiply it by x plus y. So I'm going to distribute. X squared times x is x to the third. 2xy times x will be 2x squared y. And then y squared times x will be x y squared. X squared times y will be another x squared y. 2xy times y will be 2xy squared, and then y squared times y will be y to the third. Now when I add all these up, I will get x to the third plus 3x squared y plus 3xy squared plus y to the third. All right, now a couple things that I want you to notice from this. You will notice that the powers of the x values decrease each time I go over by 1, and the powers of the y increase each time by 1 every time I go to the right 1. You'll also notice that my coefficients are 1, 3, 3, 1. And if I go back to Pascal's triangle, this third row, 1, 3, 3, 1, shows us that Pascal's triangle finds us the coefficients of these expansions. Now we can generalize that, and again, the binomial theorem, we have this equation that we're trying to do for any expansion of a natural number. So when you see this, remember it's all of the possible options where n could be any number. So if n was like 1,000, we could have 1,000 of these terms. Now the new value here is this NCR. This refers to combinations. And we can do that in Desmos, and it will calculate it. Now, if you take Intro to Stats next year, you'll see this a little bit more in counting. We're not going to go into the formula because the numbers get big real fast, and we're just going to use our Desmos to do it anyway. But basically, when I talk about counting terms, you'll notice they start counting with 0, 1, 2, all the way up to whatever n was. You'll also notice that this first variable, this first variable, the power decreases by 1 each time, and then for the b value, the power increases by 1 each time. So even though this is a fairly ugly looking equation, there are some significant patterns to it. You can see this number is constant, this number is just counting starting with 0. So how can we use that? Well, let's say you wanted to use the binomial theorem to expand 2x minus 4 all to the 5th power. Well, if we go back to this first one, you notice if I set that up, I'd have to set it up as this times this times this, and then I'd have to do it 2 more times to get the 5th power. You can see already that if I had to bring down 2 more, that thing's going to get very big very quick. But what we can do is we can use this binomial theorem. In the case that we're talking about, our n is going to be 5, and we'll start counting with 0, and we'll go up to 5 terms. So the way that I'm going to do that is I'm going to start out with 5c0, because that is my first counting term. And just like in here, it starts with n. Our n is 5. We'll start with 0, and then we're going to take this first term right here to the 5th power. So we'll have 2x to the 5th, and then we're going to take this negative 4 to the 0 power. So again, look back here. The first one is the 5th to the 0, and then we're going to change the c number by 1 added each time. We'll decrease the power of what's in the a value by 1, and we'll increase the power of the b by 1, and we'll do that till we get to 5. Alright, so it'll be plus 5, choose 1, we increase that by 1. The 2x, its power is decreased by 1. The negative 4, its power is increased by 1. We'll go 5c2. And again, the 2x, its power is decreased by 1. The negative 4 is increased by 1. 5c3. The 2x gets decreased by 1, so it's 2. The negative 4 gets increased by 1, it's 3. We'll have 5c4, 2x to the 1st, negative 4 to the 4th, and then finally 5c5, 2x to the 0, and then negative 4 to the 5th. And again, I know that I'm done because I've gone from 0 up until these two numbers are the same. All right, so now how do I calculate these things? Well, we're going to use Desmos to do that. And so just to show you how to do that, I'll come to my calculator here, my Desmos, and Desmos does it this way. It's lowercase n, uppercase C, lowercase r, and then a parenthesis with the values that you want. So if I want to do 5 chosen 2 at a time, 5C2, that'll give me that 10. Now, we want to be able to repeat this quickly, so Desmos gives us the power to make functions and use tables. So let's do that. Let's go let's go f of x is equal to NCR, and then we want to use 5, and then because that's going to be constant for us, and then we'll use an x here. And you'll notice it builds this table for us already, which is kind of nice. And so we're going to go plus, we're going to add a table, and we're going to make this y1 f of x1. And so what it'll do is anytime I plug a number in for x1, it'll plug it into this x here. So since we're counting 1, 2, 3, or 0, 1, 2, 3, 4, 5, what I'm going to do is I'm going to go back to here. I'm going to start with 0, and I'm going to go 1, 2, 3, 4, 5, and these become the values of these C expressions right here. So I can replace those, and again, my first one will be 1, my second one will be 5, the third one will be 10, the fourth one 10, the fifth one 5, and the last one will be 1 again. So here I will have a 1, and now I have to calculate this expression. So 2 to the 5th is 32, x to the 5th, and then anything to the 0 power is 1 from yesterday. 5c1 is 5, so I'll have a 5 there. 2 to the 4th. 2 to the 4th is 16, and then I have my x to the 4th, and then I have negative 4 because negative 4 to the 1st is negative 4, and then 5c2 is 10, so I'll put a 10 there. 2 to the 3rd is 8, x to the 3rd. Negative 4 squared is 16. 5c3 is 10 again. 2 squared is 4, x squared. Negative 4 to the 3rd. Well, negative 4 to the 3rd turns out to be negative 64. And I've calculated this off to the side. But if you wanted to, you could go to Desmos and come here and go negative 4 raised to the 3rd. It's either negative 64. I've done it on paper. And then my next one right here will be 5 chosen 4 is 5 again, and then I have 2x, and then negative 4 to the 4th turns out to be 256, and then 5c5 from this other page is again just 1, and then anything to the 0 power is 1, and then negative 4 to the 5th power turns out to be negative 1024. Alright, so how do I finish this up? Well, I have to multiply all of the numerical values and leave the variables. So 1 times 32 times 1 is 32x to the 5th. 5 times 16 times negative 4, and again, I've already done this calculation, but you can do it in a graphing calculator. Turns out to be negative 320 x to the 4th, and then 10 times 8 times 16 10 times 8 times 16 turns out to be 1280 x to the third. 10 times 4 times negative 64 turns out to be negative 2560. That'll be x squared. And then 5 times 2 times 256 turns out to be 2560 again, x to the first. I have no x's in the last. 1 times negative 1024 is just negative 1024. Put my box around that, and that's an expansion. Now, again, I understand that that's ugly, but just think if you had to multiply all 5 of those by hand. This still ends up being a little less work. Alright, my last example for today. Use the binomial theorem to find the 7th term in the expansion of this expression to the 10th. Now, am I going to go through and am I going to do all of this work? Heck no, I'm not going to do all this work. That would be crazy. But I am going to use these patterns that I see. I start with that number and then it goes 0, 1, 2, 3. This goes down each time. This exponent goes up each time. I'm going to use that pattern and I'm going to do it just in the first one. So I want to find the 7th term. Now if you remember, I start counting with 0. So if I go 0, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. At 6, that's my 7th term. So I'm going to use that pattern and I'm going to say that if I have a plus b to the n, then my result for any term will be NCR a to the n minus r b to the r value. So for this case that I want to do, the 7th term, I have an exponent of 10, so my n is equal to 10. My r, since it's the 7th term, in this case will be 6. And then I can just use, for a is going to be 3x and b is going to be 5. So I can just plug that into this for a given term. So I'll have 10 C6, 3x to the 10 minus 6, which would be 4, 10 minus 6, and then that 5 to the 6th, and if I make that calculation, I will have that particular term in the expansion. Alright, so let's go to Desmos and do that. Now this is going to get real big real fast because clearly 5 to the 6th power is going to be a big number. So let's go and go NCR 10 comma 6 is 210. I've got x to the 4th, but I got to take my 3 to the 4th, so let's do that. That's going to be 81. And then 5 to the 6th, that's going to be the big one. It's going to make this number pretty big. 5 raised to the 6th is 15,625. Alright, so all I got to do to finish this off is multiply those values together, and since I've calculated them all in Desmos right here, I can just go 210 times 81 times 15,625, and that is a pretty big number, but it turns out that my final answer for this ends up being 259,657,650 x to the 4th. And I know that's a big number, but wasn't really that bad to calculate using Desmos. Well, that's all I got for today, folks. So, the Mandalorian fun fact of the day, The Mandalorian has an impressive directorial team, including Jon Favreau, Bryce Dallas Howard, and Taika Waititi, who are all actors in their own sake. Jon Favreau plays Happy Hogan in the Spider-Man and Iron Man movies. Bryce Dallas Howard is the girl running from the T-Rex in high heels in Jurassic World. And Taika Waititi was the bad guy in Free Guy, and he is also the director of Thor: The Dark World. Well, that's all I got for today, folks. Have a good day. Goodbye.